I thought I would try and get across, with the aid of what I used to call a lantern slideshow, some of the great successes of the MRC, to be sure that the successes are the basis of going forward, that we don't actually forget what we've done. And so my lantern slideshow starts with the first report of the Medical Research Committee, as you see, published in 1914-15. What you don't see on it is that it cost threepence. I glanced through the report, and on page 22, there was an account of Dr. Brownlee's work. Dr. Brownlee was the statistician employed at the First National Institute. And I quote, "Some of the results obtained during the year have been published by Dr. Brownlee in the following papers. Investigation into the periodicity of infectious disease by the application of a method hitherto only used in physics." Paul will resonate with that, I hope, because in the discussions for the Francis Crick Institute, bringing physicists into the Institute is of high priority. Two further faces, Austin Bradford Hill and Richard Doll. Austin Bradford Hill was a pilot in the First World War. Luckily, he got tuberculosis because the life expectancy of a pilot was considerably shorter than that of somebody with tuberculosis. And as a result of that, he didn't do medicine, but what he did was a great favor for medicine because he invented the randomized controlled trial, first applied in the treatment of tuberculosis, and then with Richard Doll did the famous study which established the relationship between smoking and lung cancer. Note that this was an experiment in that it was not simply observational epidemiology. Doctors were studied, and those that gave up smoking fared well, and those that were heavy smokers had 20-fold risk of dying of lung cancer. Our president has already made reference to tuberculosis. Our chief medical officer has made reference to the challenge of infectious disease. When I was a child in South Wales, born in 1938, tuberculosis hung over our community like a dark cloud. Everybody knew somebody with tuberculosis. Everybody had somebody in the family with tuberculosis. I qualified in medicine in 1961 when tuberculosis seemed to be receding, although even then some of my contemporaries as young doctors were contracting tuberculosis. One of the interesting and disturbing worries I have is that I may bracket my life with being under the cloud of tuberculosis as a child and under the cloud of drug-resistant tuberculosis as an elderly gent. Two other people who stand for the MRC's enduring contribution through epidemiology are Jerry Morris, who established, by the simple epidemiological experiment of comparing the life expectancy of bus conductors and bus drivers, the importance of exercise in keeping people alive and well. And the last of my heroes of the epidemiological era is Archie Cochrane, who is known to some of us in this audience. He made attempts to teach me when I was a medical student, for he was the David Davis Professor of Tuberculosis and Chest Diseases in Cardiff between 1960 and 1969, an experience he did not enjoy, but he'd gone to Cardiff to study coal workers' pneumocardiosis as part of the MRC unit there, and later it became, with the demise of pneumocardiosis, the MRC epidemiology unit. Archie was messianic in his belief in the value of the randomized controlled trial and thought that it should be applied to things outside medicine, like politics, law, education, a whole host of things which were entirely impractical. But he actually laid the foundations of what we now know as evidence-based medicine. He acquired a belief in the futility of doctors through his experience as a doctor in a prisoner of war camp, when he came to the conclusion that anything he did was likely to make the patient worse. And that enduring pessimism carried through to the end of his days. But he was a marvelous man, very rich and very left-wing. And the last person I want to show a lantern slide of is Brian Greenwood. Now, Brian has made a major contribution to the prevention of malaria, not through molecular biology, not through biochemistry, not through anything more fancy than impregnating mosquito bed nets with insecticides, and saved the lives of literally millions of people. Now, I can't, with my Cambridge background, not say a few words about the Cambridge environment, which features so strongly in the MRC's activities. I thought you'd like to see this picture of 1964, 2 years after the LMB opened. That's the building over there on the left with a sort of house next to it, which is now the junior doctor's residence. And this is the beginnings of Addenbrooke's Hospital. As you can see, it looked a pretty windy wasteland, as indeed it was. The site was acquired for £4,900 in 1949. And the MRC located the LMB there simply because the university departments did not want to have an institute, because it would actually disturb the balance of teaching and research in their departments. I got this lovely picture of Max Perutz, which I will show you, not least because of the wonderful double helix, or whatever it is, in the building on the right. And then fast forward to 2013, the present state of the campus, with MRC LMB2 over on the left, Cancer Research Institute, and a whole host of other things built around a 1,200-bedded teaching hospital. Now, it's this campus with this mix of science and medicine which is proving to be enormously important. And as many of you will know, AstraZeneca have decided to move their research headquarters to Cambridge, and I think it's in no small part due to this mixture of science and medicine that is almost uniquely represented there, and is one of the forces, I believe, one of the many forces in the UK, which is important to keep our pharmaceutical industry here, rather than migrating to Boston, which seems to be the default position these days. Then just a word or two about monoclonal antibodies. So well known, it's hardly worth describing them, but vitally important. Around 40% of drugs in development in the pharmaceutical industry derive from the work of Cesar and Greg Winter. I couldn't resist showing you this paper, Nature, August the 7th, 1975. Look at the last two lines. Such cells can be grown in vitro in massive cultures to provide specific antibody. Such cultures could be valuable for medical and industrial use. And you know the rest. Here's a very specific example of a monoclonal antibody. Alistair Comston, professor of neurology there, used an antibody made by Greg Winter and Herman Waldman for the treatment of multiple sclerosis. This slide of the effect of treatment, the red line on the bottom there, was published in the late 1990s. The drug receives approval from the FDA later this year. There's another story there, the long duration between discovery and the application of medicine, about which we need to do something. And then there's Tiny Maney and Mark Feldman winning the Lasker Award for anti-TNF antibody, which transformed the lives of people with rheumatoid arthritis. Their work actually depended upon the biotech company, Cambridge Antibody Technology, which Greg span out and was responsible for the making of anti-tumor necrosis factor antibodies for rheumatoid arthritis, and actually another drug called Benlysta, which GSK have approval for the treatment of systemic lupus erythematosus. So now here's Sidney. You've seen him in the flesh, but I actually like him in this black and white photograph. It captures him beautifully. I went to Cambridge largely because of Sidney, and he came to the Department of Medicine, and we had a great time together. But I was on a fancy committee called ACOST when the Human Genome Project was being discussed. And I found myself in the role which many of you will know of as sort of Sidney's dog. I had to make presentations about the human genome, which I was learning fast, and eventually had to make a presentation to Mrs. Thatcher in April 1988. And I thought you might like to see my initial notes and Sidney's handwriting over the side, but much of it is reiterated today. The database will become the central tool for basic and applied research in the medical sciences, etc. The identification of human genes, their mapping can proceed now and requires only relatively small technological advances and an intermediate timescale. He went on to say it wouldn't cost very much, but that actually turned out not to be the case, at least in the short term. And then just a word or two about what it's doing to practicing doctors. This is the familiar heat map, the genomic signature, which is being applied in cancer. Unsurprisingly, cancer, being a genomic disease, is very amenable to genomic investigation. And on the right-hand side, the tumors with metastases are up on the right, and on the left, the tumors without, and you can see they're different, and you get what's called a genomic signature, which predicts prognosis. It turns out not to be that simple, though, because when you take a simple, what seems like a simple cancer, like breast cancer, and you apply genomic technology to it, you find you've got multiple cancers. And this is a great challenge in the cancer field. However, there are fantastic success stories. This is the effect of the inhibitor of BRAF. Mike Stratton discovered the BRAF mutation in malignant melanoma. Philip Cohen worked on it. What have I done here? I've lost my slide. That's not very clever. I think I've deleted the slide. Anyway, what I wanted to show you was the PET image, positron emission tomography, of the effect of a BRAF inhibitor in this particular cancer, and one of the great recent advances in cancer therapy. Oh, there it is. Just worth saying en passant that positron emission tomography was developed at Hammersmith, at the Hammersmith MRC cyclotron unit. When it was being developed, it was thought to be of no clinical interest whatsoever. It was thought to be only of interest in studying the brain, but the idea that it would be applied to things like cancer simply hadn't emerged. Now, in my last few minutes, I'll say a few more words about genomics. One of the emerging problems is that cancer turns out to be heterogeneous. One cancer can have several mutations in it. The mutations may be different in the metastasis, and it's not practical to biopsy the cancer tumor in several places, nor is it practical to biopsy, in most cases, the metastases. So this recent work, which comes from Cambridge, from Nitsa Rosenfeld and the Cancer Research Institute, is an illustration of a non-invasive method which measures DNA in plasma of cancer patients. This, I don't know what I've done to this thing. I'm sorry. That's what I wanted to bring up. This is a low-cost, high-throughput method which does amount to a non-invasive liquid biopsy for personalized cancer genomics. I bring this up to illustrate the point that medicine is intensely dependent on technology. The whole of medicine, the whole history of medicine is dependent upon technological advances. Now, this is a picture of an eye, which I've brought to show you because it represents age-related macular degeneration, commonest cause of blindness in elderly people. No treatment until recently has been available for it. But the genomic revolution discovered something very surprising, namely that there was polymorphism of a factor in the blood of the complement system, which hadn't been linked with eye disease. But this discovery ignited a frenzy of activity by the biotechnology industry into looking for anti-complementary drugs. It's a very good example of the unlikely way that medical progress advances. And then a last set of examples of genomics. We were, as Paul has said, we were all brought up on the notion that disease was a mixture of genetic susceptibility and environmental influences. But what was surprising was the discovery that one's genome was a determinant of prognosis in particular diseases. And this is work done by Ken Smith and his colleagues in Cambridge, in which they find a particular heat map, a particular genomic signature associated with certain diseases. And the extraordinary thing is that in 4 quite disparate diseases, if you have one genomic signature, you do well. If you have another genomic signature, you do badly. And of course, this has great implications for the planning and conduct of clinical trials. And then coming back to the theme of infectious disease, the other major revolution which has resulted from genomic science is the possibility of routine use of genomics in public health laboratories. And this is a recent and very interesting publication on this front from folk at the Sanger and folk in Cambridge. Now, Paul has already spoken a bit about complexity in medical science, and I can't compete with him, but I will just show you a few slides. I chanced upon this in a bookshop just a couple of days ago. This is the current issue of Foreign Affairs, The Rise of Big Data. And this complexity is actually a major issue for us all in medicine. And to my mind, the only way that we can handle it is by the promotion of interdisciplinary work, the linking of appointments in physics, chemistry, computing science, computational biology, and computational medicine. Francis Collins, the current director of the NIH, famously said the other day if he had his career over again, he'd become a computational biologist. And very importantly, we can only deal with this by removing cultural institutional barriers in the universities and our funding agencies. So the future, as you may have guessed, I hadn't actually rehearsed my talks for Sydney. The future, in my view, depends upon human biology. It depends upon experimental medicine, by which I mean the intensive study of small numbers of patients with all the technology we have at our disposal. But the remarkable thing is it's now possible to study populations in a way that was hitherto unimaginable. The 1,000 Genome Project, the Cancer Genome Project, etc. But linking that information with disease is a vital step in the process. And we are making great steps in the UK. Sally Davis is driving this to link electronic health records, to link databases in the clinic with databases in the laboratory. But that's very challenging. And I think the big challenge for the next 5 or 10 years. And finally, to reiterate what Paul has said, we need to do something about the linkage between our academic institutions and our industrial institutions. Both sides need it. The drug discovery pipeline is not as healthy as you'd expect, considering the investment in underpinning biomedical science. Now, Philip Cohen, who is here, is an exemplar of how academic science can link with industry. His unit in Dundee is a beacon for pharmaceutical companies to get access to new ideas, discovery science, in a field in which they're hugely interested. And then I thought I would just show you this introduction by Harold Himsworth for a marvelous book on the first half century of the MRC. And you see, he says, the idea that it is in the best interest of a country that research, as distinct from development, should be established independently of political interest or administrative commitment is not one that would normally occur to those concerned with the machinery of government, etc. David. And then finally, this photograph that I took myself is of the new LMB, which is being opened by the Queen tomorrow. Thank you very much.